Hey everyone, welcome to the last lesson of this week, and we're talking about Ohm's law. Um, just a quick update. Again, this is the first week back, technically, that you're allowed to come to school. I highly, highly recommend that you come in if you're having a little bit of trouble staying on top of your work, because it might just be, I know it's only for an hour and a half that you're allowed to come, but at least for that hour and a half, you're doing some pure work if you actually need to get stuff done. Other than that, we actually only have, it's probably just going to be two more lessons that I'm going to release, and then there's just going to be one big project. Not really big project, but one final project that you're going to do on the final week, and that will be it for the entire unit and for the rest of the year, because we're down to less than 2.5 weeks left in this semester, which is just crazy. We've lost most of it due to COVID. So anyways, let's get back to Ohm's law. So we're looking at some of the more practical applications in our electricity unit, and Ohm's law ends up being one of them. And before I actually talk about what Ohm's law is and how it helps us with our calculation of stuff in circuits and other stuff like that, we're just going to recall the three main terms and measures that we've been using in the electricity unit. So we have them written here. We have them written here in our table, where we were looking at current, voltage, and resistance. And so when we're looking at current, we said that the symbol for current was just a letter I. We measured current using what we called amperes, which is also just known as an amp. And our symbol for it was pretty straightforward. It's just A. So capital A for amp. So such as something like example 3 amps. That was coming out of a lamp or something, 3 amps. Then we looked at voltage. And voltage can have kind of two symbols. The most common one that we're going to actually keep looking at is just the B one. But if you choose to take electrical engineering or anything else later on in life and in school, you might see voltage is also represented as E. But that becomes more into the realm of physics. I mean, this is still physics, but for our cases, we're just going to use V because it makes the most sense. The unit measurement for voltage was volt. And again, unit abbreviation, just had a regular V. And example, 12-volt battery, right? It's kind of our power source. And then we had resistance. And resistance is one that we haven't really spent too much time on, but it's going to become important in this lesson here. So resistance, our symbol was R. And this one was measured in ohms. And this one had that weird symbol, also called omega, which kind of looks like, I don't really know, a very steep hill or a bump or a skin tag. Yeah, so we had those three quantities of measurement for our electricity so far: current, voltage, and resistance. And what Ohm did, there was a guy called, what was his name? I always mess up his name. George Ohm. George Ohm. I don't think he was French. I'm just saying it in a French way. It's probably German. And George Ohm, he discovered a relationship. And he discovered a relationship between current, voltage, and resistance. And you might be able to have some kind of an intuition on what this relationship was based off of, we're going to talk about resistance and current. But just to bring back another analogy here, so we can recall that current is basically the amount of water flowing at a given time. That's the way we can think about it. Instead of thinking about electricity flowing, we can think about the amount of water flowing, because that's a little bit easier for us to conceptualize, right? If we had a tube of water here, and we see that it gets pinched here, the current is actually, technically, it's shortened here, right? Because it's the flow of water. The flow of water is pinched down, so it's the water has less area to actually flow through. And over here, the current is larger. We have a larger flow of water going through here. So again, we can think of this as the flow of water, or amount at once, right? And this is basically our current. This is our current. Okay. And resistance, we haven't really talked about this, but resistance is basically a pushback on our current, right? When we were looking at the FET simulators with our light bulbs, you were able to have a chance to increase the resistance on the load that the light bulb gives. And what you notice is that as you increase the resistance, you essentially slowed down how many electrons were able to flow into that light bulb at once. You slowed down their overall velocity. And the same thing happened with the resistor, right? If you put down just a regular resistor and increase their resistance, you saw that the flow of electrons slowed down. And the higher you put that resistance, the more it slowed down. So in the same way, we can think of that as putting like a big ball of wool inside a pipe with a lot of flowing water. And what we see is that on our left-hand side of the wool, where the water is flowing normally, we have a pretty good flow of water. But on the right-hand side, when it's hitting that wool, we have less water coming out of here, right? We have half as much water coming out of here. So we could think of this, we can think of resistance as something which impedes or slows the flow of water / electricity. And what I'm going to do, I'm going to ask you to take a look at this table right down here. And this is basically just a table of appliances that you might find in your house. We have a lamp, laptop, and a toaster. And we have the resistance values on them measured, and we have the current values measured on them. And I want you to figure out, you can maybe pause the video right here, and figure out what the relationship is between resistance and current, because I don't think you really need to even have to graph this to see what's going on. So as we can see with our lamp, our resistance is at 150. To our laptop, it's at 60. To our toaster, it's at 20. So our resistance is going down for each appliance. And the appliance doesn't really matter. We're just concerned about these resistance values. So 150 ohms, 60 ohms, 20 ohms. But what's happening with the current? What's happening with the current? Because you might have an intuitive idea of what's going to happen. If we lower the resistance, or if we remove some of this cotton here, do you think that's going to make the water flow faster? Or do you think it's going to make it flow slower? Well, it's going to make the volume increase, right? And we can see that here. We can see that the current, I should just put this down, resistance. The current increases as resistance decreases. And whenever you see something like this, whenever you see something where it's like, okay, so as we're lowering our resistance, we're also seeing that our current is increasing. This is called an inverse relationship, because as one thing is going down, another thing is going up. As one thing is going down, another thing is going up. This is known as an inverse relationship. And these are seen all over the place. You can think about it. Well, there's a bunch of physical applications of this. But all we need to know, and all you need to concern yourself with, is that Ohm saw that there was something going on here, right? There has to be some relationship between resistance, current, and he dug a little deeper and found out that voltage also plays a big role in this. So as we're lowering our resistance, our current is increasing. Well, how does voltage play into that? And he started playing around with all of this. And what he discovered was Ohm's law. Ohm's law. And what Ohm's law states is that our voltage, let me do this a different color. Voltage was equal to our current, or yeah, we can call it current. Let's just keep it like that. Our current times, I'm going to make that a different color, stand out a bit. Our current times what? Times the resistance. So the overall voltage of the entire system is equal to the current that is flowing through that system times the resistance of that system. And what's nice about this is that we can use this to help calculate either voltage, current, or resistance in our system. So if we know two of the things in our system, we can figure out the unknown. And this becomes useful when we're actually building circuits, right? Because we've seen, and I'm sure you've experienced in that PhET simulator, what happens if the current is too large for your system. The whole thing catches fire, right? So when we're building our circuits in real life, if we know the voltage and if we know the resistance that's going through the system, we can calculate the current, and we can figure out whether that current is going to be too much or too little for our system, so that it doesn't overheat or catch fire or do anything terrible. And we can summarize this. We can summarize this relationship with a triangle. So what I'm going to do, let's do it in a different color. So let's take this, and I'm going to do a little bit of manipulation here. And what we're going to do, see if I make a perfect triangle. Oh my gosh, that was terrible. There we go. What we can do, I'm going to create a useful thing that you can use in future courses to help you remember this law. So we just have to draw a triangle that's somewhat straight. Come on. There we go. And it's going to be split into three parts here. And on top, I'm going to write our voltage, so just V. And then actually on the bottom here, we're going to write I for current, and then, oh my gosh, R for resistance. V, I, and R. And this is just going to be a helpful tool to help you figure out how to calculate voltage, current, and resistance. So I'll show you how to use this. So what we're going to say is that, well, we know that voltage is equal to I is equal to current times resistance, which is also equal to, I'm going to break these down to their symbols. So V equals I times R. Okay. And the way that we can read this is if you're told to find voltage, what you're going to do is you're going to essentially pretend that you're covering up the V. So the V is all gone. And then whatever two variables you have left, if they're beside each other like this, you're going to multiply. So we see that they're separated by this bar here. This means that we're going to do I times R or R times I. Okay. Well, then what happens? Let's see how we're going to solve for. Let's do current next. So let's say current equals, well, what does current equal? Well, let's cover up current. We'll pretend that we're covering up current. So we'll get rid of our I. And what's left? Well, we have V over R, or V divided by R, or voltage divided by resistance. Voltage divided by resistance. So we have voltage divided by resistance. So I equals V divided by R. And then lastly, again, I'm sure you can see where this is eventually going. We have resistance, and we'll remove our resistance up here. We'll cover that out because that's what we're trying to find. And you see that it's V over I, or voltage divided by current. So voltage divided by current, and we get R equals V over I. Okay. So what the homework is going to be, it's going to be fairly short. I'm not going to give you too much. All the homework's going to be is it's going to give you practice using these equations to calculate various values of current, resistance, and voltage for given circuits. So that's it for today, folks. Thank you for tuning in. I hope you have a wonderful, wonderful weekend. If you have any questions about anything that we've covered here, please let me know, and I'll get back to you. Email is probably the best way, or shoot me a question on the Google Classroom in the post. Okay, take care, everyone. Yeah, stay safe, stay healthy, and I'll see you next week. Okay, bye.